Welcome everyone to today's seminar. Today it's a pleasure to introduce Evan Kirby from the California Institute of Technology in the United States. Evan earned his bachelor's degree from Stanford University in 2004 and his PhD from the University of California, Santa Cruz in 2009. He was a Hubble Fellow at Caltech, then a Center of Galaxy Evolution Fellow at the University of California, Irvine. In 2014, he joined the astronomy faculty of Caltech. He's the recipient of the 2017 Newton Lacey Pierce Prize from the American Astronomical Society and is currently a Cottrell Scholar. Evan is originally from New Orleans, Louisiana, and he wishes us all a belated Happy Carnival. Thank you so much, Evan, for accepting our invitation. You may start when you're ready.
Thank you, Anna, and thank you very much, Anna, for inviting me. It's my honor to give the presentation here today. Yes, I am originally from New Orleans. I call it Mardi Gras, so happy Mardi Gras to all of you. I'm going to tell you today about nucleosynthesis in degenerate stars. And by degenerate stars, what I mean in this case is white dwarfs and neutron stars. I'm going to be spending most of the talk talking about how white dwarfs explode. When a white dwarf explodes, it's an event called a type 1a supernova. It's incredibly important for cosmology, and it's also incredibly important for galactic chemical evolution. At the solar metallicity, most of the iron in our galaxy comes from type 1a supernova. Now, how to explode a white dwarf is a subject of a lot of ink in the literature. And what you're looking at in this animation is one way to explode a white dwarf. So if I can just start over the movie, what happens at this time zero is that the center of the white dwarf becomes dense enough and hot enough that the carbon will ignite. And when the carbon ignites, it sends a deflagration front up to the surface of the star. And so the burning front proceeds against the gradient of density. So it's just trying to move towards the path of least resistance, which is straight towards the surface. That, as you can see, when the deflagration wave breaks out of the surface, it's gravitationally confined. What that means is that the white dwarf has a very high surface gravity. And so the explosion, once it reaches the surface, stays on the surface. And it propagates around the white dwarf to the other side of the white dwarf, to the anti-center. This shock wave then meets at the opposite side of the white dwarf, and it causes a secondary explosion. In this case, it's a detonation. And what you'll see in a moment is when that detonation occurs, it will disrupt the rest of the white dwarf. So this is a rather unusual way to explode a white dwarf. I mean, why not just start an explosion at the center of the star? Why do we have to have this gravitationally confined explosion that propagates to the other side and then has a secondary detonation? Well, it all has to do with how we think white dwarfs explode and what elements they make when they explode. So the mechanism of an explosion of a white dwarf will dictate what elements it makes, in particular, how much iron it makes, how much nickel it makes, how much calcium it makes, and so on. And one way to diagnose how white dwarfs explode is to see which elements they make and in what ratios. Now, one way to look at the explosions of white dwarfs is to directly observe them as they happen, so in a transient survey. Another way is to look at recent explosions, so look at type 1a supernova remnants, usually in the X-rays. And the X-rays can tell you how much calcium, sulfur, silicon, iron, and so on exists in these type 1a supernova remnants. However, I'm going to present a complementary approach, which is called galactic archaeology. Galactic archaeology is the study of the evidence that's left over in stars today to tell us about what their galaxies were doing in the past. And so the evidence that's left over in stars today are the velocities of stars, which I'm not going to talk about today, but also the chemical compositions of stars, which I am going to talk about today. So I'm going to be using the chemical compositions of stars that are descendants of type 1a supernova to infer how those type 1a supernova exploded. Now, they're going to hear about a handful of elements in the talk today, so I just thought I'd introduce these elements to you in case you're not too familiar with looking at them on a periodic table. The first one, the lightest one that we're going to talk about today, is magnesium. Magnesium on the Earth burns very brightly, so it's used in firecrackers. But for astronomers, it's used to infer the rate of star formation and hence the chemical evolution of a galaxy, especially when you take the ratio of magnesium to iron. Silicon, calcium, and titanium are a group of elements with magnesium called the alpha elements. On the Earth, silicon we find in computers. If you have a dental implant for, like, if you lost a tooth at one point in your life, you might have calcium and titanium in your mouth. The calcium is in your bones, and the titanium is, in this case, in this screw that will screw directly into your jaw if you need an extra tooth. However, for astronomers, we don't care about that. What we care about is that these elements are produced copiously in core collapse supernova, and also certain classes of type 1a supernova. But for the most part, these elements are made predominantly in massive stars in core collapse supernova when massive stars die. Iron, element number 26 in the periodic table. I'm showing you here quite literally an iron made out of iron. And for astronomers, what we use this for is to, especially in a ratio with magnesium and the other alpha elements, to figure out the ratio of core collapse to type 1a supernova, and hence the rate of star formation and chemical evolution. But I'm going to be using iron and other iron peak elements to determine how type 1a supernova explode. So along with iron on the periodic table, there's a lot of elements next to iron. So for example, chromium, manganese, cobalt, and nickel. These 5 elements, chromium, manganese, iron, cobalt, and nickel, form the iron peak on the periodic table. On the Earth, chromium is often used in cars. Chrome plating is a chromium layer on top of another alloy. Manganese is often used in dyes. It's very blue when it's in an oxide form. Sorry, it's cobalt. Cobalt is used in oxides to make pigments, and it's very blue when it's in an oxide form. Manganese has many purposes. So it's used to combine with lithium and to make batteries. I have a whole bunch of manganese in my garage because I have an electric car. And inside that electric car are lithium manganese oxide batteries. Nickel, in the United States, we have a coin called a nickel. It's 5 cents. And it's actually only 1/4 nickel. The rest of it is copper. But we still call it a nickel. But for astronomers, these iron peak elements are produced in type 1a supernova. And the ratio of, say, nickel to iron can tell us a lot about how that type 1a supernova exploded. And I'm going to be spending like 10 minutes going through an overview of nuclear physics to tell you how we can use the ratio of nickel to iron to infer how type 1a supernova exploded. And then finally, at the end of the talk, I just want to talk a very brief time about a globular cluster called M15. M15 has an unusual pattern in some of the heaviest elements in the periodic table, including barium. On the Earth, one of the more gross applications of barium is if you've ever had to go to the doctor to have them look at your intestines. I've had to do this once, it's very unpleasant. You have to drink this barium milkshake. And the reason that you do this is because barium is a very heavy element, it's a radio contrast. And so when they shoot X-rays through your body, the barium is very good at absorbing those X-rays, and so you can actually see your intestines. However, astronomers don't care about intestines. What they care about is various degenerate stars, like neutron stars. So barium is made in the R process, which is called the rapid neutron capture process. And one site that we know where the R process happened is neutron star mergers. And I'm going to be talking about the possibility of a neutron star merger in the globular cluster M15 in the last 5 minutes of this talk. So the outline is, first, I'm going to be spending the vast majority of the talk on talking about the progenitors of type 1a supernova. And at the end of the talk, I'll talk about the possibility of a neutron star merger in M15. I'll be using the iron peak elements to address the first topic, and I'll be using barium to address the second topic. And the alpha elements, magnesium, silicon, calcium, and titanium, they'll also play a role in there as well. So the first question, what is a type 1a supernova? Now, we know that a type 1a supernova is the explosion of a white dwarf. That's for sure. What happens is when you have a white dwarf, if you can get the carbon in the white dwarf hot enough and dense enough, it will burn. And when it burns, it's an exothermic process. And so the carbon atom next to it will start to burn, and the carbon atom next to it will start to burn. And so it's a runaway process. Once you ignite the carbon, then the rest of the carbon in the white dwarf will ignite. This we know for sure. What we don't know is a lot of other questions. For example, what is the mass of the white dwarf that explodes? Another question is, does the white dwarf explode by a deflagration or a detonation? A deflagration is a subsonic burning where the flame front proceeds at slower than the speed of sound, or a supersonic burning is a detonation where the flame front moves faster than the speed of sound. Another question we don't know is how many white dwarfs are participating in the type 1a supernova. Is it a single degenerate event where there's only one white dwarf, or is it a double degenerate event where there's two white dwarfs? Now, you've probably all learned in kindergarten or so that a type 1a supernova happens when the white dwarf exceeds the Chandrasekhar mass. So the Chandrasekhar mass is a special mass about 1.4 times the mass of the sun, where an electron degenerate gas, like a white dwarf, can no longer support itself against gravity. So if a white dwarf exceeds 1.4 solar masses, it will start to contract because it can no longer, the pressure that's provided by the electrons inside of the white dwarf is no longer strong enough to support itself against gravity. So the white dwarf will start to contract. The center of the white dwarf will get hotter and denser, and it'll become so hot and dense that the carbon inside of it will achieve the conditions necessary to ignite. And then that will disrupt the white dwarf. You get a type 1a supernova. And the picture that we're familiar with on how this happens is we have a white dwarf accreting from a red giant companion. So something like this. So a white dwarf is on the right here. It's sucking material off of a companion star, in this case, a red giant. The reason that the white dwarf accretes from the red giant is that the white dwarf has a very high surface gravity. The red giant has a very low surface gravity. And so it's favorable for material to be transferred from the red giant onto the white dwarf. That means the white dwarf is going to grow in mass. And if it grows enough in mass at the right rate, then it can exceed the Chandrasekhar mass and will explode as a type 1a supernova. Now, the way that you get a white dwarf to suck mass off of a red giant is that we start off with a binary system, two stars on the main sequence in a binary. One of the stars reaches the post-main sequence, so it becomes an evolved star. And then we have a common envelope phase where the primary star, the one on the left here, swallows the secondary star. The secondary star doesn't get disrupted, it's still there, it's just living inside of the primary star. At the end of this, the envelope of the primary star disperses, and we have a white dwarf in a binary with a main sequence companion. Now, the scenario I just described with the red giant, the secondary star, the main sequence companion, will then become a red giant eventually, and that's where you can get this mass transfer. This is called KC for the type 1a supernova. It's a Chandrasekhar mass explosion. The reason that the white dwarf explodes is because it grows in mass by accreting material from the red giant, and it reaches the Chandrasekhar mass and explodes. It's also called the single degenerate scenario because there's only one white dwarf in the system. However, this is not the only way to explode a white dwarf. Imagine now that we start off from here where we have the white dwarf in a binary with a main sequence star. Again, the secondary star, the main sequence star, leaves the main sequence. It becomes a red giant. It has a secondary common envelope phase where the secondary star now swallows the original white dwarf, and then that envelope disperses. Every time you have a common envelope phase, the binary gets tighter and tighter. You lose angular momentum from the system. And so at the end of this, what we have is two white dwarfs in a very tight binary. That's a system that's favorable for the radiation of gravitational waves to get the binary even closer and closer and closer. And eventually, those two white dwarfs can touch each other. They will actually merge together. And what happens when two white dwarfs merge together is a number of things can happen. The one thing that could happen is you could have a result where you'll have a super massive white dwarf that could even exceed the Chandrasekhar mass. In that case, that would be gravitationally unstable and will explode just like KC. So that would be called the Chandrasekhar mass double degenerate scenario, where the reason the white dwarf explodes is because it reaches the Chandrasekhar mass, actually exceeds the Chandrasekhar mass. And it's called double degenerate because there are two white dwarfs. However, there's another possibility here, which is that at the last moments of this merger, what happens is you can actually disrupt the secondary white dwarf. So the less massive white dwarf will be disrupted. They will not merge together smoothly. The secondary white dwarf will actually turn into an accretion disk around the first white dwarf. And the exact details of this accretion process will dictate how the supernova explodes. So one possibility is that the helium envelope from the secondary white dwarf can be accreted onto the first white dwarf. If that helium envelope is unstable, then it can detonate. And if it detonates, then it can send a shock wave into the center of the primary white dwarf, which will bring the temperature and density high enough to ignite the carbon inside of the primary white dwarf. This particular mechanism does not involve the Chandrasekhar mass. All it involves is a detonation of helium that's strong enough to then ignite the carbon. This is called a double detonation scenario. In the double detonation scenario, you typically explode the white dwarf below the Chandrasekhar mass. So in this case, the Chandrasekhar mass has nothing to do with the physics of the explosion. So in the double degenerate scenario, you can have a sub-Chandrasekhar mass explosion. There's even an intermediate case where you can have a sub-Chandrasekhar mass explosion with a single degenerate, only one white dwarf. So a white dwarf and a companion with a helium star. Now, galactic archaeology is really good at telling us one of these two things, the mass or the number of components. It's the mass. It's the mass. So the mass of the white dwarf dictates the elements that are going to be created. The double degenerate versus single degenerate has more to do with the delay time distribution of type 1a supernova. What galactic archaeology and the chemical elements tell us is the mass of the white dwarf. And I'll show you how. The thing that supports white dwarfs is electron degeneracy pressure. So you have so many electrons stuffed together that the Fermi sea that allows electrons to live next to each other becomes full. And when the Fermi sea is full, you cannot stuff any more electrons in there. So in a normal gas, like in this room here, I hope this is a normal gas, not a degenerate gas. If we had a free neutron, and I sure hope I don't, but if I had a free neutron in this room, then in a half-life of about 10 minutes, that free neutron will beta decay into a proton, an electron, and an antineutrino. In a normal gas, there's space. Oops, sorry, I didn't know why that disappeared. But there's space for that electron to go in between the other electrons in this normal gas. There's plenty of room in the Fermi sea to fit another electron in this room. But in a white dwarf, there's no space for that electron. And so the beta decay is inhibited. And in fact, we get the reverse process. I'm sorry that my animations aren't showing up here. Yes, there we go. We get the reverse process, which is called electron capture. The proton will be captured on, the electron will be captured onto protons inside of the white dwarf to make neutrons. So the conclusion from this is that if you have a dense white dwarf, you're going to get a lot of neutrons because the electrons in that white dwarf will be literally squeezed onto the protons. This process is called neutronization. And neutronization is very favorable in a very high density white dwarf. Now, a massive white dwarf is also very dense. So for the students who recently took a stellar structure class, you probably learned the mass-radius relationship for white dwarfs. The radius of a white dwarf goes as the mass to the negative 1/3 power. Paradoxically, as you increase the mass of a white dwarf, its radius shrinks. What that means is that the density of the white dwarf goes as the mass squared. And so as you increase the mass of the white dwarf, the density goes really, really high. So Chandrasekhar mass explosions will be very dense, and therefore they will be very neutron-rich. So if we see neutron-rich nucleosynthesis come out of type 1a supernova, we can infer that that white dwarf exploded near the Chandrasekhar mass. Alternatively, if you see not neutron-rich, neutron-poor nucleosynthesis come from type 1a supernova, you can infer that the white dwarf exploded below the Chandrasekhar mass. And so here's a diagram showing the density versus the mass of a white dwarf. And in this bluish color up here, what you're looking at is a Chandrasekhar mass white dwarf. The Chandrasekhar mass white dwarf goes all the way up to 1.4 solar masses. And you can see that there are, at the center of the white dwarf, where this is the center of the star, this is the surface of the star. At the center of the white dwarf, the densities get up to, say, 2 × 10⁹, 2 billion grams per cubic centimeter. This is a ridiculously high density. And that's exactly the kind of density where you get neutronization. And when you get to those neutronization densities, what you'll produce is neutron-rich isotopes like stable nickel. So nickel-56 is the isotope that we usually associate with supernova, but nickel-56 has just as many neutrons as protons. Nickel-56 is also unstable. It will disappear in a matter of 7 days or so. But if you have very high density white dwarf, then what you get is nickel-58. Nickel-58 is stable. If you make nickel-58, you'll still see that nickel today in long-lived stars. On the other hand, a sub-Chandrasekhar mass explosion, this orange dashed line, doesn't ever get to densities that are high enough to make these neutron-rich isotopes. Instead, you make a lot of neutron core isotopes. You can make a lot of nickel-56, which has just as many neutrons as protons. The nickel-56 decays away, but you don't get stable nickel, and you don't get manganese. Manganese is a very special isotope, very special element, because it has only one stable isotope, manganese-55. The only stable isotope of manganese has 5 more neutrons than it does protons. So if you see manganese, you know that that manganese came from a dense Chandrasekhar mass type 1a explosion. Okay, so if you didn't follow any of that nuclear physics, all you need to know is if you see stable nickel and if you see stable manganese, then what you're looking at is a Chandrasekhar mass explosion. So the whole reason I started this project is because I had all these spectra from the Keck telescope, specifically from the DMOS instrument. The DMOS instrument stands for the Deep Extragalactic Imaging Multi-Object Spectrograph. And the important part of this is multi-object spectrograph. It means I can get a whole bunch of stars in different galaxies all at the same time. And I was looking at my database of spectra and I was like, what elements haven't I measured yet? And the answer was chromium and cobalt. And so you can see, I can see absorption lines of chromium and cobalt, and also nickel. And here are some absorption lines of nickel. And the red lines are my best fit models, and the pink regions are the plus or minus 0.15 dex. So you can see I can measure chromium, cobalt, and nickel to accuracies of about 1/10 of a dex. And the chromium, cobalt, and nickel are iron peak elements, which means they're good for diagnosing the physics of type 1a supernova. So here is an example of the elemental abundance ratios that I've actually observed in an extragalactic system. This extragalactic system is the Sculptor Dwarf Galaxies, the Sculptor Dwarf Galaxy. It was one of the first galaxies discovered other than the Large Magellanic Clouds. So what you see here, sorry, I should say it was one of the first galaxies in the local group discovered other than the Large Magellanic Clouds and Andromeda. But what you're seeing here is individual stars in the Sculptor Dwarf system. Each point here represents one star, and you're looking at the magnesium, silicon, calcium, chromium, cobalt, and nickel abundances for those stars in the Sculptor Dwarf Galaxy. So I'm going to be using these abundances, especially chromium, cobalt, and nickel, to figure out how type 1a supernova explode. However, each of these elements has a contribution from type 1a supernova, but also core collapse supernova. So we have to do a short accounting problem to subtract off the core collapse component to figure out what is the type 1a component. And so in order to isolate the type 1a component of these elements, I'm going to direct your attention to the top panel, magnesium. So magnesium, so first of all, I'm going to draw a very sophisticated chemical evolution model. It's called 2 straight lines. Literally, all I did was I fit a flat line and then a slope line. That's it. This is a very, very simple chemical evolution model. And the reason that magnesium is important is that at very low metallicities, there is no contribution from type 1a supernova. So the type 1a supernova take a while to explode. The core collapse supernova explode immediately. One of the first things that happens after the first episode of star formation in Sculptor and in any galaxy is that core collapse supernova explode. So I know what the core collapse contribution of the magnesium to iron ratio is. However, type 1a supernova will start to explode around here. And as type 1a supernovas start to explode, they make very, very little magnesium. So the type 1a yield is essentially 0. This is a logarithmic scale. And so the type 1a magnesium to iron ratio is more than 2 orders of magnitude less than the core collapse magnesium to iron yield. And so what you're looking at is that as time goes on, more and more type 1a supernova are exploding, and the stars that are descended from those type 1a supernova will have lower and lower magnesium to iron ratios. So what magnesium to iron is a progress indicator from pure core collapse nucleosynthesis to pure type 1a nucleosynthesis. So I can turn this sloped line into a progress indicator from 0 type 1a supernova to a lot of type 1a supernova. This progress indicator I call F1a. It's the fraction of iron that has come from type 1a supernova. It starts at 0 when the first type 1a supernova explodes, and then it increases all the way up to above 90% by the time Sculptor is finished forming stars. So now that I have this F1a, I can go to all the other panels, silicon, calcium, chromium, cobalt, and nickel, and I can subtract off the core collapse component. And so when I do that, what I'm left over with is the green line. Once I subtract off the core collapse contribution, then what I can do is an accounting problem, and I can figure out what are these red lines tending towards? What is the type 1a nucleosynthesis? So I can infer how much silicon to iron ratio comes out of type 1a supernova. In fact, I only could have an upper limit on the silicon to iron ratio of type 1a supernova. The calcium to iron ratio is this green line. The chromium to iron ratio, the cobalt to iron ratio. You can see that type 1a supernova make very little cobalt to iron ratios. But the most important element is actually nickel. And you can see there's a very, very thin green line in this bottom panel. It's very thin because it's very precisely determined. So I've precisely determined the abundance of the nickel to iron ratio coming out of type 1a supernova to be about negative 0.3. What that means is about half of the solar ratio of the nickel to iron. And it's not just Sculptor that shows this pattern, it's also other dwarf galaxies like Ursa Minor. And I have 3 other dwarf galaxies in addition to these 2. And so what I can do here is now show you empirical yields for type 1a supernova. So each of these rainbow colored points is the empirically inferred yield for a type 1a, for all of the type 1a supernova in each of these galaxies: Sculptor, Leo 2, Draco, Sextans, and Ursa Minor. Now I can compare each of these predictions, or actually these estimates of the type 1a yield for the silicon to iron ratio, calcium, chromium, cobalt, and nickel to iron ratio for type 1a supernova. I can compare these empirical estimates to theoretical predictions for Chandrasekhar mass explosions and sub-Chandrasekhar mass explosions. Now, the theorists who blow up these supernova have all sorts of knobs that they can turn. How many ignition points are there for the supernova? What is the metallicity of the supernova that explodes? For the sub-Chandrasekhar mass models, what is the mass of the supernova that explodes? How far below the Chandrasekhar mass is it exploding? And for the first 4 elements, silicon, calcium, chromium, and cobalt, you can get almost any answer depending on how you turn the knobs. And so these 4 elements are not that constraining for determining whether or not the supernova blows up at the Chandrasekhar mass or the sub-Chandrasekhar mass. However, for nickel, you notice that all of the empirical estimates for the dwarf galaxies that I've observed are below the solar ratio. These are negative numbers, which means they're subsolar nickel to iron ratios. Now, the only theoretical predictions for subsolar nickel to iron ratios are sub-Chandrasekhar mass supernova. So let me zoom in on this. You can see that the only subsolar predictions for the nickel to iron ratio are sub-Chandrasekhar mass supernova. And all of the measurements are subsolar nickel to iron ratios. So the conclusion is that the majority type of explosion in these dwarf galaxies is sub-Chandrasekhar mass explosions. Now, I also mentioned manganese. So I showed you with nickel that the conclusion is that the majority of type 1a supernova blow up below the Chandrasekhar mass. But manganese is even more sensitive to the white dwarf mass than nickel, because remember, manganese has only 1 stable isotope, and it is very neutron rich. It has 5 more neutrons than protons. And so graduate student Mia de los Reyes at Caltech has been measuring manganese abundances for stars, the same stars for which we've measured nickel and other elements. And what she found is that the manganese to iron ratio for type 1a supernova kind of falls exactly between what you might expect for sub-Chandrasekhar mass explosions and Chandrasekhar mass explosions. So this looks a little bit ambiguous. So, I mean, the nickel seemed pretty clear it was sub-Chandrasekhar mass explosion. So why is the manganese giving us a more ambiguous result? Well, it's actually not that different if you realize that this x-axis is a logarithmic scale. And so the manganese to iron ratio here is an order of magnitude less than the manganese to iron ratio here. What that means is you don't need that many Chandrasekhar mass explosions to pull up the average manganese to iron ratio of the entire galaxy. And so what that's saying is if we actually do a linear decomposition of the sub-Chandrasekhar versus Chandrasekhar mass supernova, about 80% of this type 1a supernova in the Sculptor dwarf galaxy blew up below the Chandrasekhar mass, and about 20% blew up at the Chandrasekhar mass. And so we're seeing evidence that there's two different types of type 1a supernova, Chandra and subchandra. We can also see that when we look at different galaxies. So all the galaxies that I showed you before were exclusively ancient. All of their stars formed many, many billions of years ago. But we also have in our sample two galaxies that have extended star formation histories that formed stars as recently as 1 billion years ago. They're called Leo 1 and Fornax. And you can see that if you wait long enough, if you have a galaxy with an extended star formation history, then the nickel to iron ratio turns upwards. And that's also true for the manganese to iron ratio. It will turn upwards. So the conclusion is that if you wait long enough, then white dwarfs will start to explode at the Chandrasekhar mass. The first type 1a supernova to explode, and the only ones that you see in exclusively ancient dwarf galaxies, are sub-Chandrasekhar mass explosions. But if you wait long enough, then you'll start to see the near Chandrasekhar mass explosions. So our tentative conclusion from this work is that type 1a supernova explode in two different ways. The majority way is sub-Chandrasekhar mass explosions. But if you wait long enough, then you'll also start to see Chandrasekhar mass explosions. Okay, what I'd like to do now in the last 5 minutes or so is to talk about where the R process comes from. So at the beginning of the talk, I mentioned that I wanted to talk about the element barium in the globular cluster M15. M15 is one of the largest, more famous globular clusters of the Milky Way. It's one of the most metal-poor globular clusters of the Milky Way. And it's unusual because it has a large dispersion in the heaviest elements of the periodic table. So what are these heavy elements? Well, they're formed in what's called the R process, or the rapid neutron capture process. Where do these heavy elements come from? What explosions make these heavy elements? Well, we know for sure that the R process is made in neutron star mergers. And we know that because in 2017, in August 2017, LIGO detected gravitational waves from the merging of two neutron stars. And then electromagnetic follow-up of the light curve in the spectra of this event determined that the neutron stars created some of the heaviest elements of the periodic table: gold, platinum, selenium, ruthenium, tellurium, and barium. And the reason I'm singling out barium is that barium, of all these elements, is the easiest to measure in optical spectra of stars. And so barium is one of the best diagnostics of this neutron capture process because it's easy to measure in stars. However, there's also evidence from galactic chemical evolution modeling of the Milky Way that neutron star mergers cannot be the only source of the R process. And so it's also possible that very rare types of core collapse supernova, the death of massive stars, including stars called magnetorotational supernova, could create the neutron capture process, could create the R process. And so the question that I have is, how is this relevant to the globular cluster M15? So here's a picture of M15, a beautiful HST picture of M15. And on the right is ground-based, high-resolution measurements of individual stars in this globular cluster. Now, M15 is almost unique because it has a huge dispersion in the R process. There's a factor of 16 spread in the europium abundance of M15, a factor of 18 spread in the barium abundance of M15. This is especially impressive because if you look at iron in M15, every star has exactly the same iron abundance. So how in the world did this cluster form with all stars having the same abundance of iron and all the iron peak elements, but a huge dispersion of all of the neutron capture elements? And just to be absolutely explicit, the europium to barium ratio in M15 is plus 0.5, or about 3 times the europium to barium ratio in the sun. And the only reason I'm saying is that this proves that this is the R process, not the S process. We are looking at R process nucleosynthesis. So there is a hypothesis in the literature that I wanted to test. That hypothesis is that imagine that there was a neutron star merger in M15 that created the R process. The problem with this scenario is that neutron star mergers take a long time to form. They can take hundreds of millions of years or even billions of years to actually merge. The problem with that is that M15 formed all of its stars in a very short burst, maybe 40 million years or so. So how do you fit a neutron star merger in such a short amount of time? It just doesn't seem likely that you can actually get the two neutron stars to merge in such a short amount of time. So the scenario that's been proposed in the literature is that imagine that you had a neutron star merger happen long after the cluster finished forming stars, even billions of years after the cluster finished forming stars. Well, in that case, the stars nearest the neutron star merger would get the highest dose of the R process, and the stars farthest from the neutron star merger would get the lowest dose of the R process. And that way, you can easily explain why some stars have high neutron capture and some stars have low neutron capture. Now, you might immediately think, well, this would mean that there would be one side of the cluster that's very R process rich and one side that's R process poor. But remember, the crossing time of this cluster isn't very long. And there's been many, many crossing times since in the last billion years or so. And so what that means is that any sort of spatial inhomogeneity has now been erased by the orbits of the stars. However, stellar evolution has one weird trick that allows you to see whether or not there was this external pollution. If this neutron star merger polluted the stars that were already formed, then that R process would exist only on the surfaces of those stars. Now, when a low mass star is on the main sequence, let's say the sun is currently on the main sequence, it has a very thin convective envelope. And so when the R process falls onto the surface of the star, it becomes mixed into this very, very thin convective envelope. However, when a main sequence star leaves the main sequence and joins the red giant branch, it experiences an episode called the first dredge up. The first dredge up is when that convection zone gets very, very deep. And it becomes about half of the mass of the star. So the convection zone increases in mass by a factor of 20 or so. And what that means is that all of that material, that R process material that was dropped onto the surface of the star, is now getting diluted by a factor of 20. And so what you should see is that as a star leaves the main sequence and joins the red giant branch, you should see a drop in the R process like barium. You should see a drop in barium by a factor of 20. And this isn't just some made up theoretical scenario. This actually is real because we can see it in lithium. The lithium abundances of stars and globular clusters. So for example, the pink points here show the globular cluster NGC 6397. And this is beautiful work by Karen Lind et al. And what she's found is that when you look at the stars in the main sequence, they have a very high lithium abundance, but when they reach the first dredge up, the lithium gets diluted. Now, lithium is an element that only exists on the surface of the star. And it's because lithium is so fragile that the inside of the star was at one point too hot to sustain lithium. So the lithium only exists in the surface, and at the first dredge up, it gets diluted. So if the barium was only dropped onto the surface of the star, then what we should see is a similar dilution of the barium as the star leaves the main sequence and joins the red giant branch. And so with a new diffraction grating on the DMOS spectrograph on Keck, graduate student Gina Dugan and I observed barium in M15. And what we found is, yes, indeed, there is a large dispersion of barium at all magnitudes, at both the red giant branch and the main sequence. So we already knew that M15 had a large dispersion of barium from star to star. But what we did not see is any significant difference in the barium abundance on the red giant branch versus the main sequence. And so our conclusion is that the barium was not just polluting the surfaces of the stars. These stars were born with the R process. So all of the R process dispersion that we see in M15 was baked into the cluster from the time that it was born. This wasn't a neutron star merger that happened long after the cluster finished forming stars. So in order for the R process dispersion to be baked into M15, there's only two possibilities. One, a neutron star merger happened very, very rapidly, much more rapidly than we would have expected in M15. Or two, it wasn't a neutron star merger that made the R process. It was some rare event like a magnetorotational supernova, which would explode in a very short amount of time. And so this is still a very much open question. I would love to be able to figure out exactly how M15 has its very unusual chemical abundance pattern. And I hope that one day we'll be able to do that. Now, one survey that's going to be able to help us answer all of these questions is the Subaru prime focus spectrograph. And I think some of you there have been very much involved in this project. And I have been very much involved in this project. And I'm super excited when it achieves first light in about 2 years. Now, one reason that PFS is going to be so cool is that when we look at dwarf galaxies, just like the dwarf galaxies for which I measured the chromium, the cobalt, the nickel, et cetera, these dwarf galaxies actually occupy a pretty big portion of the sky. And so what you're looking at here is a picture of the dwarf galaxy called Fornax. You can see a very high surface brightness center at the center of this image. But there's actually member stars of Fornax that extend off the edge of this screen. So there are stars in Fornax that go way, way, way out. And the reason that those stars are interesting is if you look at their velocity dispersion, if you look at their chemical abundances, some of the most interesting stars are in the outskirts. These are the stars that can help us constrain the dark matter profile of this galaxy. These are the stars that are going to be among the most metal-poor, oldest stars in the universe. So we really want to be able to get all of the stars on the outskirts of this galaxy, not just the stars at the center. The problem so far is that spectrographs like DMOS have limited fields of view. So there's no way that you could tile all of Fornax with DMOS. It would take hundreds of nights to do it. And the situation's a little bit better with FLAMES, which is on the VLT in Chile. But with PFS, what we're going to have is 2,400 fibers distributed over 1¼ square degrees. With just 2 pointings of PFS, we'll be able to cover the entirety of the Fornax dwarf galaxy. And we're going to be able to get 4,800 stars by doing it. And so I'm really, really excited about PFS when it turns on. It's really going to be an absolute machine for galactic archaeology. And so please stay tuned over the next few years. So the conclusion of the work that I've done with DMOS is that the progenitors of type 1a supernova start off as sub-Chandrasekhar mass explosions, but they transition to near Chandrasekhar mass explosions in dwarf galaxies. And you can see that for the ancient dwarf galaxies, they had low nickel and manganese abundances, but for the galaxies with extended star formation histories, they had high nickel and manganese abundances, which you would only get from Chandrasekhar mass explosions. And at the end of the talk, I showed that there was this unusual dispersion of the R process in the globular cluster M15, but I used a quirk of stellar evolution to show that the stars were born with the R process dispersion, and they did not acquire it from some neutron star merger that happened long after the cluster formed. Thanks very much for your attention.
Thank you very much for your very didactical talk, Evan. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them on the channel, and our speaker will try to answer them later.